Hello everyone, welcome to Rail Signaling Academy. I hope you're all keeping safe. This is second part of the video to the video that we discussed last week. So in the last video, we discussed on a very high level the meaning of sighting distance and braking distance. Then we applied those concepts and discussed the headway of two aspect signaling. For two aspect, we only spoke about interstation headway, but for three aspect signaling, we went into much more detail because it's more common. So we looked into not only the interstation scenario, but also station scenario and turnback scenario. That was the end of first video. In this one, we'll be talking about four aspect headway. Again, we'll stick to only the interstation portion, and then we'll talk about hypothetical five aspect headway. Again, only the interstation scenario, and then we will dive into comparing all these headways with each other, and then I'll be discussing about disadvantages of adding more aspects. Now, going back to the definition of main signals are the one that can have danger aspect or stop aspect. So all of these can carry the stop aspect. Now, why four aspect signaling? Because in this one, we are giving four different types of information to the driver. Now, let's look at the aspect sequence. I'm following the similar format. The first scenario is the train approaches the route and all the signals are at green. As soon as the train steps into the first section, this signal downgrades to danger or stop because now there's a train in front. Now it goes over the next signal. The next signal downgrades to stop, but this one remains at stop because this train is still in the overlap. So the train would have to clear the overlap for this signal to be able to upgrade. And that's what happens in the next scenario. As soon as the train clears the overlap, this signal can finally now upgrade to yellow. Then the train moves on, goes on to the next section. Now this signal upgrades to double yellow. This signal upgrades to yellow. This stays at red. And as soon as the train now finally clears the overlap, that's when the entry signal is able to upgrade to green. Now think about this scenario for a minute. If, let's say, the train were to stop right here for some reason, what I'm telling the driver is, okay, this one's green, you're okay to go at normal speed, and then the next one is double yellow, so I'm saying caution, you are going to see a yellow signal in front of you, which also means that the one after is red. Now compare this to three aspect signaling. In three aspect signaling, I only gave driver one warning, but in this one I am giving him second warning or an advanced warning, and you'll see how that impacts headway when we talk about the mathematical formula. Looking at the time distance graph, same format. I picked up the first scenario and the last scenario. In first scenario, you have blue train approaching the section. I'm plotting it on time distance graph, and then I plot this all the way until the blue train clears the overlap, and when it clears the overlap is when the entry signal upgrades back to green, and when it upgrades back to green is when I can have the purple train approach the route. So then I plot the purple train. T2 minus T1 becomes the headway. Now you'll see that most of this looks similar to what we saw in the three aspect signaling, but there's only one number that's different, and that's 1.5. Now I want to discuss about why this number is different, and for that I'm going to bring up the three aspect scenario here on the slide. So this is the three aspect scenario, this is the four aspect scenario. Now, like I mentioned, that in three aspect I only gave single warning, whereas in four aspect signaling I gave like an advanced warning. So now I'm telling the driver with double yellow that you're going to see red signal, but it's not the next signal, it's going to be the one after. Because of that, I'm able to reduce the signal spacing. For three aspect, I had to space out signals at braking distance, whereas in four aspect signaling, I can space out signals at half of braking distance, and that reflects in the formula. In the formula, it's braking distance plus half, so 1.5 times the brake. You'll see when we discuss five aspect signaling how this can be very easily extended, this concept. Going to five aspect signaling, there is no system that I personally know of that uses this configuration with triple yellow, but the point of having this is to explain the effect of having extra aspect, that you can keep on increasing the aspects that will reduce the headway, but obviously there are disadvantages which we are going to discuss at the end. I'm going to quickly brush through this one only because it's a hypothetical scenario. It's very similar to what you saw in four aspect signaling, except now you have an extra aspect which is triple yellow. Feel free to pause if you want to understand, but by now it should be not that difficult to grasp. Looking at the time distance graph, same thing. You have to wait until the blue train clears the overlap, and that's when you can have the purple train arrive at the sighting distance. Now comes the interesting part where we'll be discussing the mathematical formula. If you see, this number has dropped to 1.3. It was 1.5 in the last one. Why? Because now I'm able to give, so this double yellow was advanced warning in 4 aspect. In 5 aspect, I'm able to tell the driver even before. So now I'm able to tell the driver that, hey, you know what? You're going to see a red signal, but it's not the next one, going to be the next after next after next, because of which now I'm able to keep the signals closer. Basically, what's going on here is that as you increase the aspects, not only the number of lamps increase, but also the number of signals increase. Now, the benefit is more capacity because the headway is dropping. However, we'll see that the benefit is not that much actually, and it is far outweighed by the complications or complexities. So here's a quick comparison of all the formulae. We discussed this in all the slides, but this is just a snapshot. When you upgrade from 2 aspect to 3 aspect signaling, you'll see that this customer specific distance goes away. But then after 3 aspect, when you go to 4 aspect, this number changes from 2 to 1.5. Then this number drops to 1.33. All of these have an effect that the headway starts getting better and better. And by better, I mean it starts reducing. The headway is now smaller, so you can have trains running closer to each other. Now, this is the graph that I plotted in Excel, but what I'm going to do is take you to the Excel and I'll discuss the different variables in that Excel file, and I'm going to also link it in the description below so that you can download it from there and play with the Excel to see how these headway numbers change. And now we'll look at the assumptions. So you'll see that the operational speed here, what I've picked is 160 kilometers per hour, and then the reaction time for driver, I have selected that as 10 seconds. Then the deceleration rate, so I picked that as 0.8, and then emergency brake rate, I picked that as 1. The units are meter per second square. Now gradient, because we saw gradient was also a portion in the headway, so the unit that I have used here is percent, and what that percent means is 1 in 100. So when I'm saying it's minus 1.5 in 100, what that means is that for every 100 meters of horizontal distance, the change in elevation is 1.5. So that gives me 1.5%. I convert that into angle using the tan inverse function. Using that, I calculate the acceleration due to gravity. Then using that, I calculate the braking distance, overlap. When I link it below, you can see all the formulae that I'm using here. And then based on that, I am calculating the headway using these formulae. You can change the variables as you like. This will give you the headway for different aspects. I have grayed out 5, 6, and 7 and 8 aspect signaling because these are hypothetical systems. I haven't seen them. So this is just to show that when you increase aspects, after a point, the improvements are only marginal. So now we are going to discuss the disadvantages of more number of aspects, and you'll see it's not just more lamps is more cost, more lamps is more maintenance, more lamps is more failures. You'll see that there's actually a lot that happens when you increase the lamps. So let's jump into it. Now the first one is signal masks become more complicated. So what happens here is that as you increase the number of lamps, then the height of the signal will increase, and as the height of the signal increases, the pole itself becomes heavier, and then all these lamps and all this assembly. And what that requires or what that demands is to have a stronger foundation. And that stronger foundation could mean a bigger foundation, a larger foundation, or it could mean a deeper foundation, or it could mean both. The thing is that foundation becomes an important part when you keep increasing the size of the signal. And the second thing is you'll see that there's this structure here, which is the platform. Why we need these structures is for the maintenance to be able to do any repairs to the signal. And as you can see, if my signal only had 2 lamps, only one platform would have been enough. But now since I have 5 lamps, I need an extra platform. And if I kept going up and if I had more lamps, I would need a third platform. And all of this makes the whole structure very complicated, very expensive, and overall very troublesome. Now let's look at the next one. Now this one is more severe, and we'll see why. Next one is structure clearance issues. On this picture here, you can see that there's only only 2 lamps or maybe 3 lamps, but you can see that if the signal had 6 lamps or 9 lamps, then it starts being dangerously close to the overhead lines. And not just the signal is dangerously close, if a maintainer has to go and fix the lamp, then even the maintainer is close to the overhead lines. So there's a certain spatial separation, or there's a certain clearance that we need to maintain for safety purposes. And when your signals get taller, that becomes very difficult to manage. The other thing, which is the second one, is as your signals get taller, there's a special consideration that needs to be taken into account. And that is, if the signal mast were to break, we do not want the mast to fall on the overhead line. So there are certain arrangements that are done to the mast so that they fall away, or they fall in a manner that they don't fall on the line. So just something to keep in mind when your signal lamps starts getting higher and higher. And then the last one is, as the signals become higher, you can see that there can be more sightline issues, because the higher the signal, the more potential there is for the surrounding structures to infringe upon clear visibility. And talking about sightlines, we'll move to the next one. Now the next one is driver sightlines. In this scenario, I'm talking about the closest distance from which driver can view the signal. This is important, first of all, at stations, because at stations you have very limited clearance, you have very limited area to play with, so you do not have a lot of room to relocate the signal, and that's where sightlines come into play. Now this driver here is able to view this 2 aspect or 2 lamp signal, but we'll see when you increase the number of lamps, then the driver cannot see the upper 3 lamps, and in order to be able to see those 3 lamps, the signal has to be far enough so that all the 3 lamps are in the vision of driver. What that means is that now my signal has to be really far, and like I said, when there's restricted clearance like stations and other areas, then there's not a lot of room to relocate the signal. I'm digressing a little bit here. Now this is the human eye, and in the human eye, this is the distribution of cone cells versus rod cells. And cone cells, which is the dotted line, those cells are responsible for the perception of color. And when we're talking about line side signals, that's the most important thing that we need to do. We need to be able to understand what those different colors are. And that's why if you look at the cone cell density, it rises astronomically as you get closer to the 0 degree, which means that when something is right in front of your eye, you have the maximum ability to differentiate between color. And as you keep going away from the 0 degree, those cone cells drop dramatically. That's why that cone of vision is very restricted. I've read texts where that cone of vision is only 5 degrees. So that is why signal sighting is not an easy topic, and signal sighting can potentially become a huge problem if you keep on increasing the aspects. Then there is one more problem. Now, as you've seen this formula so many times, what happens with this is, as I increase the number of aspects, I agree that this number keeps on dropping. It drops from 1.5 to 1.33, then it would drop to 1.25, then it would drop to 1.2. But then what happens is that as the signal starts having more aspect, I need to give driver more time to be able to interpret and understand the meaning of the signal. So it negates the whole purpose. Now this one is more secondary. Well, it could be primary, but I could not get the numbers. When you increase the number of lamps, I've tried to draw a simple circuit diagram that when you increase the number of lamps, the number of conductors in this cable that runs all the way from bungalow to signal, those number of conductors increase. And as the number of conductors increase, the size of cable, first of all, the cable itself becomes more expensive, and the size of the cable increases. And when size of the cable increases, that means now you need to have bigger duct banks. And from my experience, anytime you're dealing with civil infrastructure, the costs can go up really quickly. Now the last one, which is most important one, is that do not forget the real deciding factor sometimes ends up becoming the station headway and the turnback headway. And you'll see that in moving block systems with headways much better than conventional signaling, in those systems too, the turnback headway becomes the deciding factors for the final achievable headway for the full line. So overall, looking at all the disadvantages, it's clear that adding number of aspects is not not the solution, and that marginal improvement that you get in the capacity is far outweighed by the increased cost and the increased complexity of higher aspect signaling systems. And one of the ways to solve that is by directly transmitting the movement of authority information to the driver, or even better, to the onboard system, so that the reaction times are reduced and so that all the other aspects that come along with the physical signal are also eliminated. And we'll look at that in the next video. Thank you, and I look forward to seeing you in the next one. Please don't forget to leave your comments in the section below. Let me know how I can improve these videos, and see you in the next one.